First, I'm going to review the detector performance. And just this is a quick, most of you will probably, of course, know this, but this is just a quick reminder of how reading detectors works for the JWST instruments. We do this non-destructive up-the-ramp sampling where each pixel is sampled multiple times as charge accumulates. For NIRSpec, we have primarily two readout modes. One is sort of a traditional mode in which you read all the pixels in the sequence, including the reference pixels. For NIRSpec, the 4-pixel row and columns around the boundaries are the reference pixels and don't see the sky, but can be used to subtract off the biases. The IRS squared mode inserts extra leads of the reference pixels between sets of the normal pixels, and it jumps back and forth, and that gives you longer frame times, but much better removal of 1/f noise. Right. A more detailed summary of these results, along with the references for much of this material, is available on the JDocs pages, which just yesterday were updated for cycle 2 to contain most of this information. The first thing to say is that in many ways, the detector performance is very close to pre-launch estimates. The detectors and the ASICs attached to them did not have to be retuned for on-orbit use. And so a lot of things haven't changed, including the interpixel capacitance, the persistence, the nonlinearity, and what we adopt for at least the detector part of the quantum efficiency really haven't changed. And the bad pixel maps have changed a little bit, but they're very similar, with over 99% of the pixels being considered operable. That is, they're not either insensitive or so hot or otherwise show funny RC light curve characteristics. Right. One thing that has changed is the docks. The docks are modestly larger than the pre-launch estimates, most likely due to the on-orbit radiation environments. And this for both the traditional and the IRS squared mode. The numbers in parentheses are what the pre-launch measurements were, and the other numbers are what the launch measurements were. What we measure on orbit. You note that and all sits is an example of one of the subarrays. Now, for these near-IR instruments, the primary contribution from the docks actually is the heat generated when you're reading the pixels. So for the subarrays where you're reading things faster, you actually have a higher dock current than you do for the full frame readouts, such as traditional and the traditional full frame readout and the IRS squared. Now, this shows an example of what this looks like in the docks for the traditional mode readout. And qualitatively, the main difference is that you get this extra bright pixel frame effect around the edge of the detector. That wasn't seen on the ground, and it's presumably related to the radiation environment. But other than that, in the slight increase, the dock rates look pretty similar to what they were pre-launch. The IRS squared modes, I'm not showing you the dock image for those ones, but I am showing you what the IRS squared mode does to the 1/f noise. The 1/f noise is particularly annoying because it makes these correlated stripes that drift slowly over time as you read out the detector. And the IRS square mode jumps back, during the readout, jumps back and forth to the reference pixels, and that can largely remove this 1/f noise. And especially on the NRS1 detectors, we see it dramatically reduces the effective total noise on the detector. It does give you a larger frame readout time because the extra time to take jump back and forth to the reference pixels means, of course, that you're accumulating charge longer during the readout. This wants to be sensitive, and this is the what we call the correlated double sample noise, which is just if you do a simple correction by just comparing adjacent frames and look at the residual noise, these are slightly different scales, but you can see that the IRS squared, the typical correlated double sample noise, drops rather dramatically, while it's somewhat less so for the NRS2 detector, although there still is some reduction and perhaps a slightly broader profile than you see on NRS1. And the effective total noise combines the effects of the lead noise, the dark current, the 1/F noise, and also the cosmic rays that you get. And so this is what actually goes into the ETC calculation, and what is probably the best representation of the of what you get on orbit. And this is what we actually saw as the total noise for exposures of various lengths, is measured in orbit in some very long docks that were taken as part of the commissioning program. And it's probably better displayed on the next page, where that just shows you as a function of exposure time. And as you see, for NRS1 detector, you get a rather dramatic drop in the total noise pretty much for all exposures between the full frame traditional mode and the IRS squared mode. For NRS2, the drop isn't as dramatic, because otherwise the tuning of that detector isn't quite as good, and so you IRS mode, you get some other noise sources that compensate for the 1/F noise. But that noise is probably easier to handle than the 1/F noise, even though it may not make much of a, even though you may get similar, RMS estimates for the total noise. So we strongly recommend that everyone use the IRS squared readout mode for full frame readouts whenever it's practical. The only times, it is somewhat longer exposure time, so there might be cases where you saturate with the IRS squared mode where you wouldn't saturate the normal mode. And of course, if you have to use subarrays, we don't have this enhanced reference sampling for subarray modes. For in that case, you do have to use the more traditional readout selection. Now, the cosmic ray environment, the overall cosmic ray rate and the size of the cosmic rays are actually pretty similar to what pre-launch predictions were, except we see these additional large snowball events that weren't really anticipated. There were some kinds of snowballs seen on the ground, but those appear to have been somewhat of a different things. And actually, it's not just NIRSpec. NIRCam and NIRS, all the NIR-IR instrument detectors, see essentially the same kind of events. And they're relatively large, heavily saturated regions that appear suddenly that are several pixels across and have extended wings. And depending how you count them, you tend to get one such event every few hours, perhaps. Get more if you count smaller events as snowballs. And the one annoying thing about them is that you get this very saturated core, but that tends to, due to the interpitchal capacitance, tends to bleed out into the surrounding region over the subsequent frames. So essentially they tend to glow. They glow a bit over time. And as you see from these examples, they'll actually tend to be associated with a shower of more typical cosmic ray events in the surrounding region that generally appear at the same time as the thing. And due to the nature of these things, the large size and the tendency to, expand over time, the pipeline doesn't subtract them as well as it might. And improvements are underway to handle that. But you may see some artifacts like this in your data occasionally. Right. So that was sort of the review of the detector performance. Well, here's some the target acquisition. NIRSpec target acquisition. First thing you want to remember is that the initial pointing accuracy without target acquisition is somewhat better than pre-launch estimates. And based just on the guide stars, you get about a 10th arcsecond 1 sigma radial, assuming, of course, you properly supply the coordinates of your science target. At the moment, there's an additional offset in how we have the IFU registered with respect to the guiders, but that we should be removed well before the cycle 2 starts. And so for many IFU observations where you have a 3.1 by 3.2 arc-second aperture, and sometimes even for the X1600A1 aperture, which is a 1.6 by 1.6 arc-second fixed slit, you may consider just skipping target acquisition and going with the blind pointing, especially if you have very good target coordinates. There are actually two modes you can do to improve target acquisition. One is the wide aperture target acquisition, which essentially centers a point source in this X1600A1 aperture. And the other one is the MSA target acquisition algorithm, which as you'll see, uses a number of reference stars distributed across the MSA and does a measurement of them and minimizes the solution to get a best fit for the correction for both the roll and the pointing. You can also choose not to do target acquisition, or for IFU mode and MOS mode, you can also take a full frame image at the end of any visit to try to retrospectively measure the pointing. Right. For WATA, as I said, it centroids a single source in the 1.6 by 1.6 arc-second aperture. You have a choice of 3 subarrays and 1 or 3 filters to get a range of dynamic range in your source. And the accuracy after the WATA should be better than 20 milliarcseconds RMS. And in fact, when we compare after we do the target acquisition image, we also do a reference image taken after the target acquisition, and measuring the residual error in that, at least with respect to the point within the detector that we were aiming for, is actually much better than the 20 milliarcseconds. So your target is well centered on the detector after WATA. And sleuths to other slits should add a few milliarcseconds errors, but again, relatively small. There's a few practical caveats when you're doing a WATA target acquisition. The 1.6 by 1.6 arc-second aperture is rather smaller than for the other NIRSpec instruments, and it's also smaller than the target acquisition regions for HST instruments. So you do have to, especially with faint high proper motion targets, you do have to be sure that you actually correctly specifying the proper motion and the epoch of the originally supplied position. And for some things, especially for faint brown dwarfs, observers have discovered that their coordinates weren't quite as accurate as they thought they were going in, and that as a result, they missed the target. And unfortunately, that's usually considered to be the observer's responsibilities. So such observations are not normally repeated. So if you have any doubts about whether or not your coordinates and your proper motion are correct, you might consider taking pre-imaging to verify that the target is actually where you think it is, even for something where you're not doing, the more complicated MSATA algorithm. One other feature of the current algorithm is that the onboard algorithm, since it uses unsigned integers in its math, can actually clip faint targets at the Bayer level drifts downwards between the groups of the TA. This shouldn't be an issue if you meet the minimum signal-to-noise requirement of 20:1, but if your target is fainter than expected, you may find that it disappears in your target acquisition, and that basically the target acquisition algorithm doesn't see it. So if you have doubts, you should probably go deeper. You don't want to risk saturating the target because that can also degrade the centroid accuracy, but there's a pretty big dynamic range. So if there's any doubt, you might consider taking a longer exposure by using a larger subarray or using a higher throughput filter than you maybe need just to get the minimum 20:1 signal to noise. Now this shows the examples for the initial pointing errors, the offsets calculated during the TA for actual data. One thing we haven't done yet is to screen out the cases where the main problem was in the supply coordinates. But as you can see that after the TA, we even allowing for some of these cases where you get the larger errors, the target actually was far enough off that it appeared at the edge of the subarray. And so it's partially vignetted when you calculated the slew, and so it didn't end up as accurate. But for the bulk of the targets where they started well in the middle of the subarray, we actually get very good centering correction. And in here, of course, we get a mix of targets that the coordinates weren't quite accurate compared to the ones that were very accurate, and you met the expected centroid accuracy. Right, now the MSA target acquisition, images 5 to 8 different reference stars, both at an initial pointing and also at a different position shifted by where we take a dither of a half MSA shutter in each axis. That's so if a star is vignetted at one position, it will be unvignetted at the other position. And to a large extent, vignetting is expected to cancel between the two positions and give you, a good centroid by the time you average between them. And there's an iterative algorithm that then, rejects the outliers and finds the best solution both for the, not only for the X, the offset in, X and Y, but also for the overall role of the telescope. And it's expected that if you have a good enough catalog accuracy, you get 20 milliarc seconds RMS, or about a tenth of an MSA shutter in your overall pointing accuracy over the entire MSA region. And in JDocs, we document what the expected degradation is if your input catalog accuracy isn't quite as good. Now, one caveat is that the TA algorithm has a limited ability to correct the roll, and if the roll is too far off, the TA will even refuse to calculate it. And if you have a roll offset of more than a few arc minutes in rotation, there's a good chance you're going to fail the target acquisition. And if you only have if you're using pre-imaging, for example, and only have 1 or 2 Gaia stars to register with, it actually can be rather difficult to get the roll, to the defined precisely to 1 arc minute of rotation. So that's something you have to be careful with. Like in WATA, we take a post-TA reference image, but that we don't dither. So the accuracy from the retrospective calculation, since you only see the stars at one pointing, probably won't be quite as good as the actual accuracy of the TA itself. And this, for example, shows you the initial pointing accuracy. Here, of course, since people are much more precise about getting their catalog coordinates in the first place, we do see that we actually are well within the, the average radial offset is typically within the 10th arc second, or perhaps a bit more than you expect just from the guide star accuracy, and that even given this lower resolution of the measurement in the reference image, and the fact that some of these have fewer than recommended stars, and this is just whatever the GOs gave you for the coordinate accuracy, so they won't always meet the highest specs. But despite that, the average radial offset, residual radial offset measured after the target acquisition is only 25 milliarc seconds. So, we're actually doing pretty good in terms of the real TAs that we get on orbit for GOs, and I think there's only 1 or 2 that have actually failed because it couldn't converge to a solution. All right. All right. Now, this is just an example of a fixed slit observation we did for commissioning. We observed one target in the fixed slit with a single exposure type of exposure, but we used the option here to actually observe it in 2 different fixed slits, which will fill the gap in the wavelength coverage. So we get actually 2 exposures. In this case, we did 3 primary dither positions and subdixal spacing. So there's actually 6 total integrations for each of these 2 dither positions. So now if we look in the archive and just use the default search, and we'll restrict ourselves to the F100 LP filter to just pick out this particular the exposures. You see a bunch of files, and you might first thought might be these other different, dither positions, but actually that's not what these are at all. Each of these files is the combined exposure for, in this case, say the S200A1 over all the exposures, dither positions for that aperture. But you do end up getting these multiple, the S1, 0, 1, 2, 3, 4, 5. And what these actually are that it actually, when you expose the, when you observe with a fixed slit with a larger subarray, in this case we're using the all-slit subarray, it covers all 5 of the fixed slit apertures. And in this case, it's in addition to the point source extraction that it's doing in your selected science aperture, it's actually also doing extractions for you in all the other apertures of the sky background. And each of those appears as a separate high-level product in the archive. Unfortunately, it only gives you the name of the aperture that was being used for the science target, and you have to figure out which of these 1, 2, 3, 4, 5 actually corresponds to the aperture you wanted to observe and which ones are the background apertures. Now, if you add those to the download basket, you again just see these observations here by default, and you see again the files, the calibrated files, the cosmic ray rejected files, the 2D rectified files, and the X1D extraction. But and again, this is all just for the combined over dithers. If you want to see there's also files done for the exposure level, but if you want to see those, you have to uncheck this box that says minimum recommended products, and then just look at the science exposure, and then you'll get all these additional files which show the exposure level products appearing in your download basket. And in addition to the files you originally searched for, it'll show you all the associated files. So in this case, these first 2 files are actually the target acquisition that was done using WATA, and the reference image after the target acquisition was done doing WATA. And since WATA only uses NIRS1, you only see NIRS1. And then you also see the exposure level products for each of the spectroscopic exposures. And these actually add up to a fair number because between all the dithers and things, we took a lot of exposures. And again, here you do see that sort of the parallels, the X1D files and these distortion corrected files. But the contents of these are rather a little bit different than for the ones that are combined for, a given target in the aperture, which combines over the exposures. In the data files, the keywords aperture name and PPS aperture always show the aperture name that was listed in the primary header. So if you look at these different files, you always see that this, for example, for the S200A1. If you look at the slit name keyword, however, you'll see the actual slit that was used for each of these. One caveat here is that there's currently a bug in the pipeline where in the X1D file for these target level, combined exposures, it actually does split it's still putting the wrong keyword in. It's telling you S200A1 for everything. So you have to actually look at the other files, say the S2D file, to see which slit was actually used for that particular observation. But I do believe it's doing, it's actually extracting in the correct place. For the exposure level files, you get an X1D file for each exposure. But in this, you get, instead of doing a separate file for each aperture, it's done as a separate extension for each aperture. And you only see the extraction for that particular exposure. So if you want to look at your individual dither positions and see how the extraction looks in individual dither positions, this is where you have to look. And in this case, it actually is putting in the X1D file, it is actually putting the keyword in correctly to tell you which aperture is which. And of course, in this case, since the NIRS2 the S200B1 aperture isn't shown because this was an NIRS1 detector, we looked at NIRS2, it would show us the extraction for this other slit. Right. Now, the Mars observations are similarly organized, except in this case, this S in the file name refers to the different targets and different slitlets you've opened up on the shutter. And in the exposure level files, the source ID curve, the intent is that it matches the catalog ID number that was assigned in your MPT catalog, except when you go to the target level files, Unfortunately, they only allocated 5 digits in these file names, and so if you have something greater than 100,000, which is common, it currently replaces the number with a different. It changes the number on you, and you have to look at other keywords to figure out what the original source ID was in the catalog.